Welcome to the Explainer. Have you ever looked at a textbook full of intimidating, abstract math and thought, there has to be a better way to understand this? Well, today, we're going to gently demystify the invisible forces of electricity. We're going to take those dense equations and transform them into a structured, fascinating story of a working system. I'm really glad you're here. So let's get comfortable and dive in.
Think about this for a second. How do we actually measure something we can't even see? That is the fundamental challenge of electrical engineering. Every single day, you interact with this incredible force. I mean, it's literally powering the device you're using to listen to this right now, but you can't see it with your own eyes. So how did engineers figure out exactly how to quantify, measure, and ultimately control this invisible power?
Here's our roadmap for today. We'll start with the foundations of flow. Then we'll compare direct versus alternating current. From there, we'll look at power and energy, introduce what I like to call the circuit cast, and finally, map out the rules of traffic.
All right, part one, foundations of flow, the absolute smallest conceptual pieces.
Before we can even think about building a complex circuit, we have to zoom way in, right down to the atomic level. And that brings us to our absolute first core concept, charge. Simply put, charge is just the characteristic property of fundamental particles. Protons carry a positive charge, electrons carry a negative charge. We measure this property in units called coulombs. It's the absolute baseline. Without charge, we literally have no electricity.
Once we have that charge, the very next question is, what happens when it moves? That's electric current. Now the equation is I equals dq over dt. If you aren't a huge fan of calculus, please don't let that intimidate you. The d just represents a tiny change. So in plain English, current is just a tiny change in charge over a tiny change in time. It's the rate at which those electrical charges flow. You can think of it as the speed of the traffic on a highway, and we measure this flow in amps or amps.
But here's the thing. Those charges, they're not going to move on their own. They need a reason to flow. That's where electrical potential or voltage comes in. Voltage is the amount of work required to move a unit of positive charge from one place to another. Think of voltage as the driving force. It's the necessary push or electrical pressure that forces those electrons down the path. And it's measured, as you might guess, in volts.
Moving right along to Section 2, direct versus alternating current, basically how this flow moves over time.
Because once we have that current being pushed by voltage, it doesn't always travel in exactly the same way. The actual shape of the flow matters immensely. There are two main categories you need to know. Direct current, or DC, is the straightforward one. It flows uniformly in a single direction with a constant value. It's perfectly steady, kind of like a calm river. On the flip side, we have alternating current, or AC. AC is cyclic. It flows in a positive direction and then reverses to flow in a negative direction, back and forth over and over again.
You can see that exact difference beautifully illustrated here. On one hand, you have direct current, just a perfectly flat, unbroken horizontal line showing a constant value over time. Then compare that to the alternating current. You see that beautiful sinusoidal wave? That's visual proof of AC peaking in the positive, crossing the zero line, dipping into the negative, and returning. This cyclic, repeating, back-and-forth nature, that's exactly what allows us to transmit power over vast distances, and it's what powers most of our electrical grid today.
Let's transition to Section 3, power and energy, the capacity to do work. So, we've established our fundamental flow, current, and our driving force, voltage. What actually happens when you multiply them together? Well, you get real-world utility. But we really need to make a crucial distinction here between power and energy. Electrical power, measured in watts, is the product of voltage and current. P equals V times I. This is the rate at which work is being done right in this exact instant. Electrical energy, on the other hand, is measured in joules. Energy is the total work done over a period of time. A great way to think about it is this. Power is how fast your car is driving right now, while energy is the total number of miles you've covered by the time you reach your destination.
That brings us to Section 4, the circuit cast, introducing the physical elements.
Up until now, we've been talking entirely about invisible forces and mathematical concepts. Now let's actually meet the physical cast of characters that engineers use to control those forces on a real circuit board. We can classify these elements into two distinct camps. First, we have our active elements. These are our voltage and current sources, things like batteries and generators. They're the components that actually supply energy to the circuit. Then we have our passive components, resistors, inductors, and capacitors. These elements don't generate power themselves. Instead, they consume it, dissipate it, or temporarily store the energy that was provided by the active sources.
Let's dive a little deeper into one of those fascinating passive elements, the capacitor. Notice how elegantly we can see the relationship between our invisible variables over time. When a constant rectangular pulse of current is applied, just watch what happens. You see the charge steadily accumulating in a linear line, and right alongside it, the voltage rises in perfect proportion. Finally, you can see the energy stored in the capacitor sweeping upward on a curve. It proves visually that as charge piles up inside this physical component, the potential and the stored energy grow in direct response. It's really quite beautiful when you map it out.
And now we arrive at Section 5, the rules of traffic, how these elements behave together.
We know how the flow works, and we've met the elements that manipulate it. But how do they behave when they're actually interconnected? Well, to navigate a circuit, you first need to understand the map. A node is simply the point where two or more branches connect. Think of it as a street intersection. A branch is a direct path between two nodes, the street itself. And governing the traffic on these streets is Ohm's law, V equals I times R, meaning the current flowing through a conductor is directly proportional to the voltage applied across it, balanced out by the resistance. It is hands down the single most foundational law of electrical engineering.
But Ohm's law isn't the only rule on the road. We also have Kirchhoff's laws, which are essentially the absolute rules of circuit traffic. First up is Kirchhoff's current law, or KCL. It states that the algebraic sum of currents meeting at any node is exactly zero. Basically, whatever traffic flows into the intersection absolutely must flow out. Second is Kirchhoff's voltage law, or KVL. This states that the algebraic sum of voltages around any closed loop is zero, meaning all the energy supplied by your active sources is going to be completely dropped or used up by the passive components in that specific loop.
Let's look at KCL in action to make it super concrete. Here we have a simple junction with 5 different paths meeting at a single central node. Following the standard convention, arrows pointing in are positive, arrows pointing out are negative. The math elegantly balances them out. The currents entering the node must absolutely equal the currents leaving the node. It's a perfect system of accountability. No electrons are being spontaneously created or magically destroyed at that junction.
And here we see Kirchhoff's voltage law applied to a simple loop. You have a source voltage and 3 resistors. If you trace the loop, the equation shows that the source voltage minus the drops across the 3 resistors equals exactly 0. Or, said another way, the sum of the applied voltage equals the sum of the voltage drops. Every single volt provided by the battery is perfectly accounted for as it works its way through the circuit. Engineers use these simple, predictable loops to set up matrices and solve for literally any unknown in an entire network.
When we pull back, the grand picture really starts to emerge. Circuits are composed of just 6 basic types of ideal elements, 3 passive, 3 active. And because these governing laws, Ohm's, KCL, KVL, obey strict mathematical principles, they are fundamentally linear. So the absolute key takeaway here is this. No matter how immensely complicated a modern computer motherboard or a massive city power grid looks, it is ultimately just a scalable combination of these basic elements following these perfectly linear, predictable rules.
Which brings us to our final thought. If wildly complex circuits are truly just these simple, peaceful rules scaled up, what invisible machines will you build next? Electrical engineering really doesn't have to be an intimidating mountain of math. It's a highly logical, highly accessible toolkit for creation. Once you understand the flow, the cast, and the rules of traffic, you have everything you need to harness the invisible. Thank you so much for learning with me today. I hope this explainer has sparked some curiosity and given you a peaceful confidence in the brilliant basics of electrical engineering.